AP Calculus, section 6.4, page 2. We are starting right here at d squared y over dx squared is 5x squared plus 1, and we recognize that as being a second derivative. And to find a second derivative, that is the derivative of the first derivative. So I've rewritten this equation as d dx of y prime, or d dx, the derivative of the first derivative. And then let's go ahead, like we did on page 1, and separate out the variables. So we have dy prime is 5x squared plus 1 dx. Then we'll go ahead and anti-differentiate both sides by doing an integral. The right-hand side, very straightforward. That is going to be 5/3 x cubed plus a 1x plus a c. Left-hand side, not as nice. I would like, because you don't recognize it very well. Come up over here and let's look at this one. What if I gave you the integral of, like, say 6 dx? Well, you know that that would be 6x plus a c. What if, though, I made it like this, just dx, the integral of dx? Well, isn't that the integral of a 1 dx? Well, that's got to be 1x plus c, or just x plus c. How about this? What's the integral then of y? Shoot. Not y dy, just dy. I was thinking about the answer. That is y plus c. And let's take it one more. Integral of a d theta. That's just theta plus c. All of that now, what does that tell you about over here? The antiderivative of the dy prime, that's just y prime plus a c, but we know that c is on the other side. Now, this y prime right here, well, that's dy dx equals 5/3 x cubed plus an x plus a c. And then let's separate the variables. Pull this 5x up over here. Anti-differentiate both sides. Left-hand side, y plus c, but that c is on the other side. Over here, when we anti-differentiate this side, let's see, where it's going to be an x to the 4th. Divide by that new exponent, that's going to give us a 5/12 here, plus the antiderivative of an x, half x squared, plus, now don't get too upset about this constant. See, that's a constant, like a 6 or a 2 or a 9. And the antiderivative of that is just the constant times x, so cx, then plus another constant. These are different constants. They might be the same, but more than likely they're not. So we do need to differentiate between them. That one of them is a c sub 1 and the other one a c sub 2. This is our complete solution right there. Now, a couple of things before we do part 6 is you could have done this way, way back at the beginning of this chapter, and we never would have separated out the variables. You would have started with y double prime as this 5x squared plus 1, and then you would have just very intuitively gone backwards. The antiderivative of that, 5/3 x cubed plus an x plus a constant, and one more going backwards. Same thing. Okay, so why did I take you through this long way? Just to reiterate that separating out the variables. But I need you to pause the video after I finish my sentence here and look at the difference in number 5 compared to the difference of questions 1 through 4 on page 1. Seriously, pause the video, go look. What's the difference between the setup for number 5 versus the setup for questions 1 through 4, besides the fact that number 5 is a second derivative. Thank you for going and looking. You noticed that questions 1 through 4 all have a derivative that is dependent on x and y, or I don't think there's any y's alone, but this one is dependent only on x. So if your differential equation is dependent only on x, then all of this separating out the variables, not necessary. Again, let me say that again. If your derivative or differential equation is dependent only on x, then separating the variables is not necessary. If that derivative differential equation is dependent on x and y, or solely dependent on y, then you must separate out the variables. Okay, going on then and looking at number 6 here, I want you to find the particular solution. That's the C's. The particular solution is finding the C's. Finding the, oops, I gotta move it down for you. Finding those plus C's. All right, so we will use this information right here. Y is 4 and dy dx is a third when x is 2. So I'm going to come right here into this y prime. I'm going to put that back up here. dy dx, that's y prime, 1/3 when x is 2. So we have 5/3 times 2 cubed plus 2 plus a c. Okay. Let's see, 8 times 5, 40. So we have 1/3 is 40/3 plus a 2 plus a c. Subtract that 40/3, that's negative 39/3, which is negative 13, which means c is a negative 15. All right, now, because we started here, we have to follow that c through and see if it got adjusted at all. So that c, same as this c, same as that c, same as that c, same as that one. It didn't get multiplied by 2 or divided by 3 or anything or changed. So this is actually c sub 1, which is a negative 15. Now we're going to go into this final line down here, and let's use x is 2, y is 4 to figure out what c2 is. So y is 4. We have 5/12 times 2 to the 4th plus a half times 2 squared minus 15, there's your c1, times 2 plus c2. Let's see, 5/12 times a 16. Let's see, I'm going to divide by a 4 here. That's going to make this a 4 and that a 3. That's 20/3 plus 4/2, 2 minus 30 plus a c2. There's minus a 28 plus a c2. I'm going to add that 28 over. That's 32 over here. I'm going to change this to an improper fraction, 6 2/3. I'm sorry, that's not improper. I'm going to change it to a mixed number. And c2 is, let's see, 32 minus 6, 26 minus 2/3, 25 1/3. Okay, so there's your last constant, but we're not done. The last bit is you have to put all these constants back into this equation. I'm going to have to kind of write it sideways down here because I'm out of space. So your final answer is going to be y equals 5/12 x to the 4th. You see that? Yeah. Plus 1/2 x squared minus 15x plus 25 1/3. Although if you would like to leave that as 76/3 for that final constant, you may as an improper fraction. There's your final answer for number 6. Okay, moving on and talking about exponential growth and decay. Exponential growth and decay are models where the rate of change of the amount of a substance with respect to time is proportional to the amount of substance at a given time. Okay, so this rate of change, that's a derivative. The rate of change, dy dt, rate of change of the amount of a substance with respect to time. So dy dt, that is, there's your equal sign, proportional to the amount of substance. So there's your constant, proportional to times the amount of the substance, y. That's the general format that we're going to use. In general, t is time, y is the amount of the substance, okay, that substance could be bacteria, it could be money, it could be rabbits in a population, it could be the value of your car, it could be carbon-14 for a half-life, all kinds of stuff that can be, it's lots of stuff going on. And K is a constant. Y is the amount of our substance. It must be positive. Can't have a negative number of bacteria. Time must be, and it can't be 0, because if there's nothing there to start with, it's not going to grow or decay. If time must be 0 or larger, can't have negative time. We also know if K is greater than 0, then we're looking at exponential growth. And if K is less than 0, then we'll be looking at exponential decay. And anytime you see the word models with math or applications with math, then we are looking at word problems, your favorite. Please join me on page 3 and I'll take you through an example of exponential growth and decay.